So angular momentum, we need to deal with angular momentum, and the inspiration for it is classical. You have L is R cross P, classically. So let's try to just use that intuition and write the various operators. And in fact, we are lucky in this case. The operators that we would write inspired by the classical definition are good operators and will do the job. So what do we have? Lx, if you remember the cross product rule, that would be y pz minus z py. Now you can think of these things as cyclic, like a circle in which you have x and px, y and py, and z and pz. Things are cyclically symmetric. There's no real difference between these coordinates. So you can go cyclically here. So you say, let's go cyclic on this index. Ly is equal to the next cyclic to y in that direction is z px minus x pz, and Lz is equal to x py minus y px. And these things, I'll think of them as operators. Let's put hats to everything. The first thing I could wonder with a little bit of trepidation is maybe I got the ordering wrong. Should I have written, here classically you put R cross P, and then the order of these two terms doesn't matter. Does it matter quantum mechanically? Happily, it doesn't matter, because Y and PZ commute. Z and PY commute, so you could even have written them the other way, and they're good. All of them are unambiguous. You could have even written them the other way, and they would be fine. But now these are operators. And moreover, they are Hermitian operators. Hermitian. Let's see, Lx dagger. Well, the dagger of two operators, you would do pz dagger, y hat dagger. Recall the dagger changes the order, minus py dagger, z dagger. Now, p and x's are all Hermitian operators, so this is pz y minus pyz. And we use again that y and pz commute and z and py commute to put it back in the standard form. And that's again Lx. So it is a Hermitian operator. And so is Ly and Lz. That means these operators are observables. That's all you need for the operator to be an observable. And that's a very good thing. So these operators are observables. Li's are observable. But there are funny properties with these operators. They're not all that simple in some ways. So next, we have these operators. Whenever you have quantum operators, the thing you do next is compute their commutators, just like we did with x and p. We wanted to know what that commutator is. We want to know what is the commutator of this L operator. So we'll do Lx with Ly. Try to compute the commutator. So Lx is y pz. Let me forget the hats for simplicity, minus z py. And Ly is zpx minus xpz. Okay, here is a y. The y commutes with everything here, so the y doesn't care. The pz gets stuck with the z and doesn't care about this, so this term just talks to that term. And here, the zpy, the py doesn't care about anybody here, but the z, well, doesn't care about that z, but it does care about this pz. So the only contribution, there could have been 4 terms out of this commutator, but only 2 are relevant. So let's write them down. Ypz with zpx minus, and minus, it's a plus, zpy xpz. Well, you can start peeling off things. You can think of this as a single operator with this too, and it will fail to commute with the first, so you have ypz zpx. That's all this commutator gives. And the same thing here. This fails to commute just with pz, so the x can go out, x zpy pz. And then here the y actually can go out, doesn't care about the z, goes out on the left. Not that it matters much here, but that's how using the commutator identities does. And this py can go out, it must go out on the right. zpz. I'm basing this on these identities in which you have A, B, C commutator, and then A, B, C commutators, how things distribute. Now, this is minus IH bar. And this is IH bar. So here we get IH bar xpy minus ypx. See, everything came out in the right position. And you recognize that operator as LZ. So this commutator here has given you Lx with Ly equal IH bar LZ. It's a very interesting and fascinating property that somehow you were doing this commutator, it could have been a mess, but it combined to give you another angular momentum operator. Now, it looks like a miracle, but physically it's not that miraculous. It actually has to do with the concept of symmetry. Symmetry transformations, if you have a symmetry transformation, and you do commutators between those symmetry operators, you must get an operator that corresponds to that symmetry. Or you must get a symmetry at the very least. So if we say that a potential has spherical symmetry, that suggests that when you do operations with these operators that generate rotations, you should get some rotation here. And alternatively, although again this is suggestive, it can be made very precise, when you do rotations in different order, you don't get the same thing at the end. Everybody knows if you have a page and you do one rotation and then the other, as opposed to the other and then the first one, you don't get the same thing. Rotations do not commute. A single rotation does commute in one direction, but rotations in different directions don't commute. That is the reason for this equation. And this equation, as we said, everything is cyclic. So you don't have to work again to argue that then Ly, Lz going cyclic must be equal to IH bar Lx. And that Lz Lx must be IH bar Ly. And this is called the quantum algebra of angular momentum. In fact, it is so important that this algebra appears in all fields of physics and mathematics, and all kinds of things show up. This algebra is related to the algebra of generators of the group SU2, special unitary transformations in 2 dimensions. It is related to the orthogonal group in 3 dimensions, where you rotate things in 3-dimensional space. It is here the algebra of operators, and in a sense, it's a deeper result than the derivation. It is one of those cases when you start with something very concrete, and you suddenly discover a structure that is rather universal. Because we started with very concrete representation of L's in terms of Y, P's, and all these things, but then they form a consistent unit by themselves. So sometimes there will be operators that satisfy these relations, and they don't come from X's and P's, but still they satisfy that. And that's what happens with spin angular momentum. The spin angular momentum operators will be denoted with Sx, for example, and Sy will have IH bar spin in the z direction, and the others will follow. But nevertheless, nobody will ever be able to write spin as something like that, because it's not, but spin exists. And it's because this structure is more general than the situation that allowed us to discover it. It's a lot more general and a lot more profound. So in fact, mathematicians don't even mention angular momentum. They say, let's study they classify the subject of Lie algebras is the subject of classifying all possible consistent commutation relations. And this is the first non-trivial example they have, and they studied their books on this algebra.